Look closely at a sunflower, and you'll notice something strange. Its seeds spiral outward in perfect curves, following an ancient mathematical rhythm. Now tilt your head toward the night sky, and you'll find that same spiral etched into the arms of distant galaxies. This isn't a coincidence, it's a whisper from the universe itself, a hint that everything from the smallest leaf to the largest cluster of stars might be woven together by invisible threads of symmetry. For centuries, scientists, philosophers, and artists have chased these hidden patterns, convinced that beneath the chaos of the cosmos lies an elegant order waiting to be uncovered. What if the universe isn't just random? What if it's built on a secret code, a symphony of shapes, numbers, and symmetries that repeat from the quantum realm to the edges of space? Think of the last time you stared at a snowflake. Its delicate branches aren't just beautiful, they're a blueprint, a tiny fragment of a much grander design. Crystals grow in geometric lattices, planets orbit in harmonic ratios, even the atoms in your body vibrate in precise frequencies. These aren't accidents, they're clues. From the sacred geometry of ancient temples to the spiraling DNA inside every cell, the universe seems obsessed with patterns. But why, who, or what wrote these rules into the fabric of reality? Some believe these symmetries are the fingerprints of a deeper intelligence, while others argue they're the inevitable outcome of cosmic physics. Either way, one thing is clear: the universe is hiding something extraordinary in plain sight. That's where we come in. Today, we're unraveling 30 of the most astonishing theories about the universe's hidden symmetry, ideas that will stretch your imagination and challenge everything you thought you knew. We'll explore how black holes might encode information in perfect geometric shapes, how the Big Bang could have left behind echoes of mathematical harmony, and even whether our entire reality is a projection from a higher dimensional pattern. This isn't just science, it's a detective story on the grandest scale, and you're invited to piece together the evidence. So buckle up. By the time we're done, you'll never look at a sunflower or the night sky the same way again. The same mathematical pattern that makes a seashell curve in perfect harmony also stretches across the cosmos. Meet the golden ratio, approximately 1.618, a number so precise it's been called nature's fingerprint. When you split a line so the longer part relates to the smaller, just as the whole line relates to the longer part, you've uncovered this ancient proportion. Now zoom out. Swirling galaxies like the Whirlpool Galaxy don't just resemble seashells, they mirror them, their arms expanding in near-perfect golden spirals. Even hurricanes, those monstrous engines of chaos, often spin in the same mathematical rhythm. But here's where it gets eerie. Uncoil a strand of DNA, and you'll find its twists measure 34 angstroms long by 21 angstroms wide. Those numbers, consecutive entries in the Fibonacci sequence, where each number is the sum of the two before it, a sequence intimately tied to the golden ratio. Astrophysicist Mario Livio spent decades studying this phenomenon, asking whether it's mere coincidence or something deeper. His work reveals something startling. When you overlay the golden spiral on images of galaxies, the fit is uncanny. It's as if the universe has a favorite shape. Critics argue these patterns emerge simply because it's the most efficient way for energy to flow or matter to organize, like soap bubbles forming perfect spheres. But others wonder why this ratio specifically. From Egyptian pyramids to Renaissance art, humans have instinctively gravitated toward it, as if recognizing some hidden harmony. Whether it's proof of a grand design or just nature's preference for elegant solutions, one thing's undeniable: the golden ratio whispers to us from the smallest cells to the grandest galaxies, stitching the cosmos together with invisible mathematical thread. If the golden ratio feels like nature's favorite pattern, then supersymmetry might be its ultimate balancing act. Picture the universe's tiniest building blocks as dancers in an endless cosmic ballet, quarks whirling alongside electrons, photons gliding through space. Now imagine each of these particles has a hidden twin, a mirror image partner waiting in the wings. That's the bold promise of supersymmetry, or SUSY for short, a theory so elegant it could rewrite physics as we know it. Here's the twist: particles come in two flavors: bosons, the social butterflies that carry forces like light and gravity, and fermions, the introverts that make up matter. SUSY suggests every fermion has a boson superpartner and vice versa. Electrons would pair with selectrons, quarks with squarks, photons with photinos. These twins aren't just theoretical. If they exist, they could solve one of science's biggest puzzles: dark matter. CERN Large Hadron Collider has spent years smashing protons together at nearly light speed, hunting for whispers of these elusive superpartners. Think of it like shaking an invisible tree, hoping something tangible falls out. So far, the detectors haven't caught them. But why? Some physicists argue we just haven't reached high enough energies yet, like trying to bake a cake at too low a temperature. Others whisper an even wilder idea. What if these particles are so heavy they warp space-time itself, hiding in dimensions we can't yet perceive? The stakes couldn't be higher. If SUSY is real, it wouldn't just balance the cosmic books, it could reveal why the universe has exactly the right mix of forces to allow stars, planets, and us to exist. Without these hidden twins, the math of particle physics collapses into ugly, unstable equations. Yet with them, everything clicks into place, as if the universe were designed with a mathematician's precision. Whether SUSY remains a beautiful dream or becomes a groundbreaking discovery, one thing's certain: the search for symmetry is far from over. Now picture reality as an illusion, a breathtaking cosmic magic trick. What if everything you see, touch, and experience in 3 dimensions is nothing more than a hologram, a shimmering projection from a flat, 2-dimensional surface at the edge of the universe? This isn't science fiction, it's the holographic principle, one of the most radical theories in modern physics. The idea sprouted from a paradox about black holes. When an object vanishes into one, does its information disappear forever? Quantum mechanics says no, information can't be destroyed, but if it escapes, how? Enter Leonard Susskind and Gerard T. Hooft, who proposed that black holes don't swallow information, they encode it. Imagine the event horizon, the point of no return, as a vast pixelated screen. Every atom, every photon that falls in gets imprinted onto this 2-dimensional surface like a cosmic fingerprint, the 3-dimensional universe we perceive. Just a reconstruction, like a movie projected from data stored on a flat disk. The implications are staggering. If a black hole can store the entire universe's information on its boundary, could our reality be doing the same? Some theorists suggest the entire cosmos operates like this, with the Big Bang's afterglow acting as the ultimate projector screen. Even your thoughts, your memories, might be shadows cast from a flat, information-rich surface at the edge of spacetime. Critics argue this reduces existence to a glitchy simulation, but supporters counter with math equations that balance perfectly when treating space as a hologram. Experiments are underway too. Scientists are studying the cosmic microwave background for pixel-like irregularities, hunting for proof that reality has a resolution limit like a screen. Whether the holographic principle holds or not, it forces us to confront a haunting possibility. The universe might not be as deep as it seems. What we call reality could be the grandest illusion of all. What if every particle in our universe has an opposite twin, not just in charge but in time itself? CPT symmetry, one of physics' most sacred principles, suggests just that. This fundamental rule states that if you flip a particle's charge, mirror its position, and reverse the flow of time, the laws of physics should stay perfectly unchanged. At first glance, it's a mathematical curiosity, a quirk of quantum equations, but dig deeper and it hints at something staggering: the possibility of an entire anti-universe, identical to ours yet running backward through time like a cosmic rewind. Take the humble electron. Its antimatter counterpart, the positron, has the same mass but flips the charge from negative to positive. Now imagine doing that to every particle in existence, then flipping space like a reflection in a mirror, and finally reversing time's arrow. According to CPT symmetry, the resulting universe should behave exactly like ours. Some theorists, like Nobel laureate Roger Penrose, take this even further. His conformal cyclic cosmology proposes that the distant future of our universe, where everything has expanded into cold, featureless darkness, could mathematically reset into a new Big Bang, birthing a fresh cosmos where time once again flows forward. Picture it like a phoenix cycle of universes, death and rebirth stitched together by symmetry. Critics argue this is more poetry than physics, but the math holds up. Experiments with neutral kaons, exotic particles that decay differently when their charge and parity are flipped, show eerie agreement with CPT's predictions. And if an anti-universe exists, it would explain one of cosmology's biggest mysteries: why there's so much more matter than antimatter in our observable universe. Perhaps the missing antimatter isn't missing at all. It's just hiding in a parallel cosmos unfolding in reverse. Visualize this cosmic dance with a split screen. On one side, our universe expands from a hot, dense singularity, stars igniting, galaxies spinning, life evolving. On the other, its mirror image contracts toward a big crunch, time flowing uphill, broken cups reassembling on tables. It's a dizzying thought. Yet if symmetry truly governs reality, the universe might not just have a hidden twin. It might need one. Hidden deep in the mathematical wilderness lies a number system so strange most physicists avoid it: the octonions. Unlike the numbers we use daily, these exist in 8 dimensions, twisting and folding in ways that defy intuition. Yet this bizarre numerical landscape might hold the key to string theory's greatest mystery: why our universe requires extra dimensions to make sense of reality's deepest laws. String theory suggests everything from gravity to light arises from tiny, vibrating loops, but there's a catch. The math only works if these strings dance through 10 dimensions, not the 4 we experience. Where are the missing 6? Some researchers believe octonions act as a bridge, their 8-dimensional structure naturally encoding the geometry these hidden dimensions demand. Physicist Cole Fiore made a stunning breakthrough when she mapped known particles to octonion math. Electrons, quarks, even the elusive Higgs boson suddenly aligned like puzzle pieces snapping into place. It's as if nature had been whispering in octonions all along, we just weren't listening. Visualize it like this: imagine plucking a guitar string. The note you hear depends on how it vibrates, up, down, fast, slow. Now picture that string vibrating not just in space, but through octonion geometry. Each unique vibration could correspond to a different particle, with the extra dimensions folded up so small we never notice them. It's the difference between seeing a telephone wire as a one-dimensional line versus realizing it's actually a cylinder when viewed up close. Skeptics argue octonions are too unstable for real-world physics. Their multiplication rules change depending on the order you use, a property called non-associativity. But supporters counter that this very quirk might explain quantum weirdness, where particles exist in multiple states until observed. The debate rages, but one thing's certain: if octonions truly underpin reality, we're glimpsing a cosmic code far more intricate than anyone imagined, a symphony written in 8 dimensions. Garrett Lissey's E8 model is the kind of idea that makes physicists either gasp in awe or shake their heads in disbelief. At its core lies something called the E8 Lie group, a monstrously complex mathematical structure with 248 symmetries, a pattern so intricate it's been called the most beautiful object in mathematics. Lissey's audacious claim that this single geometric shape could unify all the forces of nature, from the gravity-bending planets to the magnetism clinging to your fridge. Imagine taking every known particle and force in the universe: quarks, electrons, photons, even the elusive Higgs boson, and arranging them like ornaments on a cosmic Christmas tree. Now picture that tree isn't just decorative, it's alive, its branches vibrating with the pure language of symmetry. That's the E8 model. SUSY mapped known particles onto specific points in this 8-dimensional lattice, and the fit was startling. Suddenly, electromagnetism, the strong and weak nuclear forces, even gravity, all seemed to emerge naturally from the geometry of E8, as if the universe were solving a Sudoku puzzle written in dimensions we can't see. But here's where things get heated. Critics argue the model is too pretty, that its elegance doesn't guarantee reality. Where are the experimental predictions? Where's the testable evidence? SUSY counters that E8 structure naturally includes particles we haven't discovered yet, like those that might explain dark matter. He points to the Large Hadron Collider, where new data could either breathe life into his theory or relegate it to the shelf of beautiful but unproven ideas. Then there's the visualization, a kaleidoscopic web of 248 points interconnected by lines, resembling a snowflake designed by a higher dimensional artist. This isn't just math, it's art whispering secrets about reality's fabric. Supporters see it as a Rosetta Stone for physics, while skeptics call it a modern-day epicycle, a clever but ultimately wrong solution to a deeper mystery. The debate rages, but one thing's undeniable. SUSY's work forces us to confront a haunting question. What if the universe isn't just governed by equations, but by geometry, a silent, shimmering symmetry waiting to be decoded? Whether E8 is the final answer or just a stepping stone, it reminds us that the hunt for unity is far from over, and sometimes the most controversial ideas are the ones that push science forward. Some of the most profound breakthroughs in physics happen when we realize two seemingly unrelated things are secretly the same. That's exactly what happened in 1997 when physicist Juan Maldaisner uncovered an extraordinary link between two worlds. Picture this: on one side, a warped 5-dimensional universe where gravity bends space into strange, hyperbolic shapes. On the other, a flat 4-dimensional realm where quantum particles buzz around like fireflies. Maldaisner's bombshell: these aren't just different descriptions, they're mathematically identical. One is the mirror of the other. This is the AD/CFT correspondence, a concept so revolutionary it's been called the holographic principle on steroids. Here's how it works. Imagine a vast hollow sphere like a cosmic snow globe. Inside, the anti-de Sitter space or AD/S curves inward, its walls stretching toward infinity. Now paint equations on the surface of that sphere, describing how particles interact in a quantum field theory, the CFT part. Mind-bendingly, those flat surface equations don't just approximate the 5D bulk, they are the bulk, rewritten in a lower dimension. It's like discovering the entire plot of a novel is hidden in its cover art. Why does this matter? For decades, gravity and quantum mechanics have refused to play nice. But Maldaisner's work suggests they might be speaking the same language after all, just in different dialects. Black holes become the ultimate test case. In the 5D bulk, a star collapsing into a black hole is a messy, violent event. But on the 4D boundary, it's just information rearranging itself like data being shuffled between hard drives. Suddenly, Hawking's famous paradox where black holes seem to erase information gets a potential solution. The data isn't lost, it's been translated. Visualize this with a thought experiment. Picture a block of ice melting into water. The molecules inside the ice, the bulk, behave differently than those on the surface, the boundary. Yet both are H2O, same substance, different states. AD/CFT proposes reality works similarly. The quantum fields we measure in labs could be surface ripples of a deeper gravitational ocean. Not everyone's convinced, of course. Some argue anti-de Sitter space is too idealized, our universe expands outward, not inward. But the math is too elegant to ignore. From quark collisions to superstring vibrations, Maldaisner's duality keeps revealing hidden connections. It's as if the universe left us a Rosetta Stone and we're just beginning to decipher it. Whether this correspondence holds in our cosmos or not, one thing's clear. Sometimes the most profound truths hide in plain sight, whispered between dimensions. Take your hand and trace the jagged edge of a snowflake under a microscope. Now pull back, way back, until that same jaggedness mirrors the silhouette of a distant mountain range. This eerie repetition isn't just a trick of perspective. It's a fractal, a shape that echoes itself across scales, and some scientists believe the entire universe might be built this way. Forget the idea of smooth, continuous space. Picture instead a cosmic coastline, infinitely crinkled, where every zoom inward reveals the same chaotic beauty. This is scale symmetry, the radical notion that the cosmos repeats its patterns like a hall of mirrors, from the frenzy of quantum foam to the sprawling web of galactic superclusters. The late mathematician Benoit Mandelbrot first spotted these ghostly echoes in nature. His eureka moment came while analyzing cotton price fluctuations data that should have been random. Instead, he found the same jagged patterns whether he looked at daily, monthly, or yearly charts. The universe, he realized, loves self-similarity. Coastlines, river networks, even the branching of your lungs all share this fractal quality. But Mandelbrot didn't stop there. He dared to ask, what if the universe itself is a fractal, not just parts of it, all of it? Visualize this by imagining a video zooming into a fractal fern. At first, you see delicate leaves. Zoom closer, and each leaf resolves into smaller copies of itself. Keep going, and the pattern never ends. Now replace that fern with the cosmos. Galaxy clusters resolve into galaxies, which resolve into star systems, then planets, then molecules, each level a near-perfect echo of the one above. Astronomers have even found eerie evidence. The distribution of galaxies in a 10 million light-year slice of space looks statistically identical to a chunk 10 times larger. It's as if someone hit copy-paste on the universe's architecture. Critics argue this can't be literal, that gravity and quantum physics break the pattern at extreme scales. But supporters point to quantum foam, where spacetime itself churns with fractal turbulence at the smallest scales. String theory's extra dimensions might even fold up in fractal ways, like a cosmic origami repeating its creases infinitely. The debate rages, but one thing's certain. If the universe is fractal, it means there's no true zoom level where reality becomes smooth or simple. Every scale is as rich and tangled as the last, a never-ending labyrinth of self-similar wonder. So next time you stare at a tree's branches or a bolt of lightning, remember, you might be glimpsing the universe's deepest secret, that what we call scale is just an illusion, and the great cosmic design is playing the same melody on every instrument from the quark to the quasar. Whether this fractal symmetry holds all the way up or down remains an open question, but the mere possibility invites us to see the cosmos not as layers of separation, but as a single, infinite tapestry woven with threads that repeat, but never exactly, across the grandest and tiniest of canvases. Flip a coin enough times and statistically, it should land heads up exactly half the time. But the universe played a different game, one where matter somehow won against antimatter in a cosmic coin toss, leaving our reality overflowing with galaxies, planets, and us. This bizarre imbalance is called Barrian asymmetry, and it's one of physics' greatest unsolved puzzles. If the Big Bang created equal amounts of matter and antimatter, why did nearly all the antimatter vanish? The answer might lie in three brilliant conditions proposed by Soviet physicist Andrei Sakharov, rules so precise they read like a recipe for existence itself. Sakharov's first condition demands that the universe must have processes where matter and antimatter aren't perfect mirror images. Think of it like a seesaw with one side slightly heavier, tiny imbalances that add up over time. Particle accelerators have actually spotted this in action. certain quarks decay unevenly, producing matter particles a fraction more often than their antimatter counterparts. It's as if the universe has a hidden bias written into its code. Next, Sakharov insisted there had to be a moment when the cosmos fell out of equilibrium, a dramatic departure from symmetry's rigid order. Picture a snow globe shaken violently, its glitter swirling chaotically before settling. The early universe's rapid expansion provided exactly this, a hot, seething plasma where particles collided and decayed faster than equilibrium could restore balance. In that frenzy, matter's slight edge got locked in, like footprints hardening in cooling lava. Finally, Sakharov's third condition requires interactions that don't conserve baryon number. A fancy way of saying matter must be able to appear or disappear under extreme conditions. Proton decay, predicted by grand unified theories but never observed, would fit this bill. Some theories suggest ghostly neutrinos might hold the key, interacting with matter in ways that tilt the cosmic scales. To grasp the stakes, watch simulations of matter-antimatter annihilation particles and antiparticles meeting in bursts of pure energy. Had symmetry held, the universe would have been a fleeting fireworks show, snuffed out in a blaze of mutual destruction. Instead, for every billion annihilations, a single matter particle survived. That 1 in a billion fluke is why you exist. The hunt for Sakharov's conditions continues, from underground neutrino detectors to spacecraft mapping the cosmic microwave background. Each experiment brings us closer to answering the ultimate question. Why is there something rather than nothing? The answer, it seems, is written in the fine print of broken symmetry. Time seems absolute, an arrow flying relentlessly forward from the Big Bang. But what if the early universe didn't experience time the way we do? Roger Penrose's daring theory of conformal symmetry suggests that in its first fleeting moments, the cosmos might have been scale invariant, a place where shrinking or stretching space and time left the laws of physics unchanged. Picture a fractal where zooming in or out reveals the same patterns, or a musical piece that sounds identical whether played at double speed or half. That's conformal symmetry, reality's indifference to scale. Penrose's vision hinges on a radical reset. As the universe expands toward heat death, all matter eventually dissolves into massless particles like photons. At this point, distances and durations lose meaning. A photon doesn't experience time, and its wavelength stretches to infinity. Now rewind to the Big Bang's first instant, a similar sea of massless energy where scales were equally meaningless. Penrose argues these two extremes, the infinitely stretched and the infinitely compressed, are mathematically identical. The end of one universe could seamlessly birth another, with conformal symmetry bridging the gap like a cosmic Ouroboros. The proof might hide in plain sight. Astronomers studying the cosmic microwave background, the afterglow of the Big Bang, found eerie concentric circles where temperature fluctuations are suspiciously regular. These patterns, some argue, are gravitational wave imprints from collisions of supermassive black holes in a previous universe. It's as if the cosmos left fingerprints on its own rebirth. Skeptics dismiss the circles as statistical noise, but Penrose's team counters with detailed simulations showing such rings would naturally arise from conformally symmetric resets. Imagine tracing the rings like tree rings, each set marking a cosmic cycle. If true, our universe isn't the first edition, just the latest in an infinite series, each conformally linked to the next. The implications are staggering. Dark energy's mysterious acceleration, perhaps momentum from a prior universe's expansion, the low entropy at our Big Bang. A natural consequence of conformal recycling. Even time itself might be an emergent illusion, with the true cosmic clock ticking only during the asymmetric Middle Ages of each cycle. Whether Penrose's circles hold up or fade under scrutiny, one thing's clear: conformal symmetry forces us to rethink beginnings and endings. The universe might not have started with a bang, but with a whisper, a silent, scale-less moment where all of reality was just a single, infinite note waiting to be played. Imagine the early universe as a boiling cauldron of pure energy where every particle moved at light speed, unburdened by mass. Then, in a cosmic blink, everything changed. This transformation wasn't caused by some external force, it came from within, as something called the Higgs field shifted from a state of perfect symmetry to one of broken balance. Picture a waterfall frozen mid-cascade. At high temperatures, water flows freely, symmetrical in its motion. But when temperatures drop, that symmetry shatters. The water crystallizes into ice, locking into rigid, jagged forms. The Higgs field underwent a similar phase transition just fractions of a second after the Big Bang. As the universe cooled, this invisible energy field froze into a new state, and in doing so, it fundamentally altered the fabric of reality. Here's how it works. Before the Higgs field symmetry broke, particles like electrons and quarks had no mass. They zipped around at the speed of light, indistinguishable from photons. But as the field crystallized, it created a kind of cosmic molasses. Particles swimming through it began to drag, as if moving through sticky honey. The more a particle interacted with this field, the heavier it became. Electrons, relatively lazy swimmers, ended up with a modest mass. Top quarks, thrashing violently, became some of the heaviest particles known. Photons, meanwhile, slipped through untouched, remaining massless and swift. This selective resistance is why we have everything from lightweight neutrinos to ponderous protons, a diversity of mass arising from a single, elegant mechanism. The math behind this is even more fascinating. The Higgs field is described by a Mexican hat-shaped potential, a valley with a central peak. In the ultra-hot early universe, the field balanced precariously atop that peak, symmetric but unstable. As temperatures dropped, it rolled down into the valley, choosing one direction at random. This spontaneous breaking of symmetry is what physicists call the Higgs mechanism. It's like a pencil standing perfectly on its tip, theoretically possible, but the slightest disturbance sends it tipping irreversibly to one side. Once the Higgs field settled, it generated the masses of particles through interactions we now observe in particle colliders. CERN's discovery of the Higgs boson in 2012 was a landmark moment, a fleeting ripple in the field that confirmed this decades-old theory. But the implications run deeper. Without this broken symmetry, atoms could never have formed, stars wouldn't ignite, life as we know it would be impossible. The universe would have remained a formless soup of massless particles, forever racing at light speed. Yet here we are, proof that symmetry isn't just something to admire, it's something that must sometimes break for complexity to emerge. So the next time you feel the weight of your body in a chair or watch an apple fall from a tree, remember, you're not just experiencing gravity, you're witnessing the aftermath of a cosmic revolution, a moment when symmetry faltered and the universe gained its substance. Picture an ant crawling along a garden hose. From far away, the hose seems like a simple one-dimensional line. The ant can only move forward or backward. But zoom in close and suddenly the ant has a new option. It can circle the hose's thin, curled-up dimension, tracing a spiral path too tiny for us to see. This is the essence of Kaluza-Klein theory, a brilliant idea from the 1920s that dared to suggest our universe might have hidden dimensions, and that one of them could explain electromagnetism itself. Theodore Kaluza, a little-known mathematician at the time, sent a letter to Einstein with a wild proposal. What if gravity and electromagnetism weren't separate forces but different facets of the same phenomenon? Kaluza showed that if you rewrote Einstein's equations for general relativity in 5 dimensions instead of 4, an extra term appeared, one that perfectly matched Maxwell's equations for electromagnetism. It was as if the universe had been whispering its secrets in a higher dimensional language all along. But where was this 5th dimension? Oscar Klein, building on Kaluza's work, proposed it was compactified, curled up so tightly it was effectively invisible. Imagine blowing up a balloon. From a distance, it's a smooth sphere, but press your nose against it, and you'd see the rubber's texture, tiny folds and wrinkles that were always there, just too small to notice. Klein calculated this extra dimension might be as small as the Planck length, a scale so minuscule that even the most powerful particle colliders can't probe it directly. For decades, the idea languished until string theory revived it with a vengeance. Modern versions of Kaluza-Klein theory suggest not just one but 6 or 7 extra dimensions, all compactified in intricate shapes called Calabi-Yau manifolds. These hidden geometries could determine everything from particle masses to the strength of fundamental forces. Picture tuning a guitar. The way strings vibrate depends on the guitar's shape. Similarly, the notes played by vibrating strings in higher dimensions might manifest as the particles and forces we observe. The implications are dizzying. If Kaluza and Klein were right, then every point in our familiar 4-dimensional spacetime could house an entire hidden universe of tiny, coiled dimensions, like a vast library where each book contains folded pages no one knew to open. Skeptics argue there's no direct evidence, but supporters point to unexplained symmetries in particle physics that align eerily well with higher dimensional math. So next time you flip a light switch, consider this. The electricity flowing through the wires might owe its existence to a dimension you'll never see, a secret twist in spacetime's fabric, curled up so tightly it's woven into the very laws of nature. Whether Kaluza-Klein theory is the final answer or just a stepping stone, it reminds us that sometimes the universe's greatest mysteries aren't hidden in the distant cosmos but right beneath our noses, or in this case coiled inside every point in space. 2 particles separated by light years of empty space move in perfect unison, not through some invisible signal, but because reality itself has stitched their fates together. This is quantum entanglement, a phenomenon so bizarre Einstein famously called it spooky action at a distance. At first glance, it seems to shatter classical symmetry, where cause and effect should respect the cosmic speed limit of light. But look closer, an entanglement might reveal a deeper, stranger kind of symmetry, one that doesn't play by the rules of locality. Imagine tossing a pair of dice where one always lands showing the exact opposite of the other, no matter how far apart they roll. Now replace those dice with electrons, their spins forever linked even if you fling them to opposite ends of the galaxy. Measure one as up, and its twin instantly becomes down, as if space and time were mere suggestions. This isn't just statistical correlation, it's a fundamental thread binding the universe at its seams. The real twist comes with the ER equals EPR conjecture, a radical idea from physicists Juan Maldacena and Leonard Susskind. They proposed that entangled particles aren't just mysteriously linked. They're connected by microscopic wormholes, tiny bridges woven into spacetime's fabric. Picture 2 black holes entangled like particles, their interiors joined by an Einstein-Rosen bridge, the ER part. Now shrink that scenario down to quantum scales. Every entangled pair, from electrons to photons, might be tethered by similar spacetime threads, too small to see but fundamental to reality's structure. Visualize the cosmos as a vast, knotted tapestry. Each thread represents an entanglement, weaving particles together across unimaginable distances. Tug on one thread here, and somewhere else instantly, imperceptibly, the fabric adjusts. This isn't magic, it's geometry. The math suggests these connections could explain why entanglement appears to bypass light speed limits. Information isn't traveling through space, it's taking a shortcut through spacetime's hidden folds. Critics argue this remains speculative, a beautiful metaphor without direct proof. Yet experiments keep adding weight to the idea. When physicists create entangled particles in labs, the correlations hold no matter how far apart they're separated, as if space itself were irrelevant. Some theorists even suggest spacetime might emerge from a deeper network of quantum entanglements, like a 3D hologram projected from entangled qubits on a 2D surface. Whether ER equals EPR holds up or not, one thing's clear. Entanglement forces us to rethink symmetry's very definition. Instead of balanced mirrors or repeating patterns, we're dealing with a universe that stays connected in ways that defy distance, where particles separated by light years dance to the same silent rhythm. It's not that the universe has lost its symmetry, it's that we're only beginning to see its true, non-local shape. For centuries, astronomers operated under one core assumption, that on the largest scales, the universe looks roughly the same in every direction. This cosmological principle suggests a grand symmetry where matter spreads evenly like flour sifted through cosmic space. But what if that's just an illusion? Modern telescopes have begun peeling back the curtain, revealing a cosmos far lumpier and more unpredictable than we ever imagined. Start with the so-called axis of evil, a bizarre alignment in the cosmic microwave background that makes zero sense under traditional symmetry. When scientists mapped the afterglow of the Big Bang, they expected randomness, tiny temperature variations scattered like static. Instead, they found a pattern, hot and cold spots eerily aligned along a specific plane, as if the universe had a preferred direction. It's like walking into a room where confetti from a burst balloon didn't scatter randomly, but somehow arranged itself into arrow shapes pointing northeast. The name axis of evil isn't hyperbole, it's a tongue-in-cheek admission that this discovery threatens cosmology's foundational assumptions. Then there are the voids. Imagine the universe as a block of Swiss cheese, where galaxies cluster along the rinds of enormous, empty bubbles. Some of these voids stretch hundreds of millions of light years across regions so barren you could fire a telescope beam straight through them and hit almost nothing. The Sloan Digital Sky Survey revealed structures like the Hercules Corona Borealis Great Wall, a filament of galaxies over 10 billion light-years long. That's roughly 1/10 the observable universe, a scale so vast it defies the idea of statistical homogeneity. If the cosmos were truly symmetrical, these megastructures shouldn't exist. Critics argue these anomalies are just flukes that zoom out far enough and the averages smooth out, but the data keeps piling up. Galaxy surveys show webs of matter clumping in fractal-like tendrils, with some regions nearly empty and others dense as urban skylines. Even dark matter, the invisible scaffolding of the cosmos, appears to gather in uneven halos, tugging galaxies into lopsided arrangements. So what does this mean for symmetry? It might not be a fundamental law but an emergent property, a statistical mirage that only appears when you ignore the fine details, like declaring a forest uniform because from space its treetops blend into a green blanket, while on the ground sunlight dapples unpredictably through gaps in the canopy. The universe's true architecture could be far wilder, a place where symmetry exists not as a rigid rule but as a fleeting whisper in the chaos. Whether these flaws overturn the cosmological principle or just refine it remains hotly debated. But one thing's certain, the deeper we look, the more the cosmos resists our tidy assumptions, revealing instead a tapestry of magnificent, messy asymmetry. Magnets are frustratingly social creatures. Cut a bar magnet in half, and instead of isolating a north or south pole, you get two new magnets, each with both poles stubbornly intact. This seems like an unbreakable rule of nature, but in 1931, physicist Paul Dirac made a startling prediction. What if particles carrying just a single magnetic charge, pure north or pure south, existed? These hypothetical entities, called magnetic monopoles, aren't just scientific curiosities. Their discovery would rewrite the textbooks, proving a hidden symmetry in Maxwell's equations that's been staring us in the face for centuries. The math is eerily elegant. Maxwell's equations, which describe how electricity and magnetism intertwine, look almost perfectly symmetrical. Electric charges exist as isolated positives or negatives, but magnetism, always dipoles. That asymmetry has nagged physicists for generations. Dirac realized that if even one monopole existed somewhere in the universe, it would explain why electric charge comes in discrete packets. His calculation revealed a mesmerizing link. The product of a monopole's magnetic charge and an electron's electric charge must be a whole number multiple of Planck's constant. It's as if nature left a secret equation in the margins, hinting at a deeper unity between forces we thought were separate. For decades, the hunt for monopoles turned up empty. Then came the Mo-Edel experiment at CERN, a detective story unfolding in a labyrinth of particle detectors. Unlike its flashier neighbor, the Large Hadron Collider, Mo-Edel isn't smashing protons, it's quietly scanning for monopoles that might emerge from collisions or even wander in from space. In 2016, researchers spotted something peculiar: tracks in plastic detectors that could only have been made by a heavily ionizing particle with a single magnetic charge. The data wasn't conclusive, but it sent ripples through the physics community. Imagine the implications: a lone North Pole skating through a detector, leaving a trail like a cosmic bowling ball crashing through pins. Visualize a universe where monopoles roam freely. In the searing heat of the early cosmos, they might have formed as space-time itself crystallized, like cracks spreading through freezing ice. Some theories suggest they're unimaginably dense, each one a knot in the quantum fabric so tight it warps space around it. Others propose they're hiding in plain sight, trapped inside bizarre materials called spin ices, where tiny magnetic moments arrange themselves into emergent monopole-like excitations. The stakes couldn't be higher. Finding a monopole wouldn't just complete a symmetry in Maxwell's equations. It would hint at a grand unified theory where all forces emerge from a single, perfect symmetry at the dawn of time. Every failed search narrows the possibilities, but every unexplained blip on a detector reignites the dream. Whether Dirac's prediction proves true or not, the quest for monopoles reminds us that sometimes the universe's most profound secrets hide in the gaps between what we see and what we've yet to imagine. Most universes have a clear starting point, a fiery Big Bang erupting from infinite density. But the Torb-NUT universe plays by different rules. Picture a cosmos that never began, one where time isn't a straight line but a spiral staircase winding endlessly in on itself. This bizarre space-time solution, dreamed up by mathematicians Abraham Torb and Ezra Newman, trades the singularity of a Big Bang for something far stranger, a gravitational vortex spinning eternally like a cosmic carousel. At its heart lies the NUT singularity, not the edible kind, but a twist in space-time so peculiar it makes black holes look simple. Think of it as a geometry hiccup where the fabric of reality gets twisted like a Möbius strip. Run your finger along a Möbius strip surface, and you'll return to your starting point after one loop, but upside down. The NUT singularity does something similar with time. Travel far enough along its gravitational currents, and you might find yourself back where you started, not just in space, but in time. Your personal clock rewound as if the universe hit rewind. What makes this geometry so unsettling is its lack of a birth cry. No explosive beginning, no horizon of ignorance shielding a singularity. Instead, the Torb-NUT universe hums along smoothly, its rotation bending time into closed loops. Photons trapped near the singularity could orbit forever, tracing paths that look like infinite corkscrews when viewed from afar. It's as if someone took Einstein's equations and added a hypnotic swirl, turning the cosmos into a gravitational hall of mirrors. Critics argue such solutions are mathematical curiosities too perfectly symmetrical to describe our messy, expanding cosmos. But supporters counter that the Torb-NUT metric might describe regions within a larger universe, like eddies in a river where the usual rules momentarily bend. Some even speculate these twisted zones could form naturally near ultra-dense objects, creating pockets where time behaves like a record stuck on repeat. Visualize this universe not as a story with a beginning, middle, and end, but as an Ouroboros, a serpent eternally eating its own tail. The absence of a Big Bang doesn't imply stillness. Instead, it suggests a cosmos where rotation is fundamental, where time's arrow curls back on itself like smoke rings in zero gravity. Whether such a universe could ever truly exist remains unknown, but its very possibility forces us to reconsider an uncomfortable truth. Maybe beginnings and endings are just constructs, and the cosmos has always known how to dance in circles. Black holes were supposed to be the universe's ultimate vaults, places where information entered but never escaped. Then Stephen Hawking turned that idea on its head. He showed that black holes aren't eternal. They slowly evaporate by emitting what we now call Hawking radiation. But here's the catch: this radiation appears completely random, carrying no trace of whatever fell in. It's as if you burned a library full of unique books and all that drifted up from the ashes were identical blank pages. This is the black hole information paradox, a crisis at the heart of physics where quantum symmetry, the sacred rule that information can never be destroyed, collides violently with gravity's grim appetite. Picture a black hole forming from a collapsing star. As matter crosses the event horizon, all its intricate details, the spin of electrons, the flavor of quarks, even the handwritten notes in your old diary seem lost forever. According to Hawking's math, the radiation leaking out over eons would be thermal, featureless, like the hum of a quiet heater. No fingerprints of the original material. No way to reconstruct what vanished. Quantum mechanics insists this can't happen. Every particle interaction, no matter how chaotic, must be reversible in principle. The universe keeps perfect records, even if we can't always read them. But black holes, they seem to be shredding the receipts. This paradox sparked a decades-long battle between gravity and quantum theory, with some physicists arguing for radical solutions. Leonard Susskind and Gerard T. Hooft proposed one of the boldest, the holographic principle. They suggested that all the information swallowed by a black hole isn't really lost, it's smeared across the event horizon like quantum graffiti, preserved in a scrambled but perfect two-dimensional code. Imagine taking a 3D movie and compressing it onto a flat DVD. The holographic principle claims reality does this naturally, with black holes acting as extreme examples. When matter falls in, its information gets painted onto the surface, while Hawking radiation slowly peels those pixels away over time. To visualize this, think of a black hole evaporating over billions of years. Each photon of Hawking radiation carries not random noise, but a single pixel of the original data, like a cosmic jigsaw puzzle being disassembled one piece at a time. Far from destroying information, the black hole is performing the universe's most extreme file compression. The catch: you'd need the ultimate decoder ring, a complete understanding of quantum gravity, to reconstruct the original. Experiments are now testing these ideas. Quantum simulators use ultra-cold atoms to mimic black hole dynamics, watching how information scrambles and reemerges. Some even suggest that the paradox isn't a flaw in our theories, but a clue, a sign that space-time itself is emergent, stitched together from entangled quantum bits. Every time a black hole evaporates, it might be teaching us that the universe's deepest symmetries aren't written in the stars, but in the way reality keeps its secrets. Neutrinos are already the universe's most elusive particles, ghostly visitors that pass through entire planets like they're not even there. But what if some of them are even stranger? What if certain neutrinos don't just ignore matter, but vanish entirely, slipping into a hidden dimension or even a parallel universe? This isn't science fiction, it's a serious hypothesis born from some of the most baffling data in modern physics. The mystery begins with a phenomenon called neutrino oscillation. Neutrinos come in three known flavors: electron, muon, and tau, and they constantly morph between these states as they travel. But experiments like Mini Buoni at Fermilab have spotted anomalies that don't fit this tidy picture. After firing beams of muon neutrinos across a detector, researchers found way more electron neutrinos appearing than the standard model predicts. It's as if someone kept adding extra puzzle pieces to a box that was supposed to be complete. One compelling explanation: sterile neutrinos, a hypothetical fourth flavor that doesn't interact with matter at all, not even through the weak force. These phantoms wouldn't just be shy, they'd be completely invisible to our detectors. But here's where it gets wild. Some theorists propose these sterile neutrinos aren't just hiding in our universe, they might be slipping into another one entirely. Picture a neutrino oscillating between our reality and a mirror world, a parallel cosmos with its own particles, forces, even stars and galaxies, all perfectly symmetrical to ours but forever out of reach. The math behind this is eerily elegant. If sterile neutrinos exist, their oscillations could create interference patterns, like ripples from a stone tossed into a pond overlapping with ripples from a stone tossed into a parallel, unseen pond. The extra electron neutrinos detected in mini-Buani might be the faint echoes of this cosmic crosstalk. It's as if we're seeing shadows cast by particles dancing between dimensions. Critics argue these anomalies could stem from unaccounted-for experimental errors or undiscovered physics within our own universe. But supporters point to other oddities, like the so-called reactor-antineutrino anomaly, where nuclear reactors produce fewer neutrinos than expected. Could the missing neutrinos have oscillated into sterile states, vanishing into the cosmic background? The implications are staggering. If sterile neutrinos bridge our world to another, they might be the first tangible evidence of a multiverse, not as distant bubble universes, but as a mirror realm coexisting right alongside us, separated only by the thinnest of quantum veils. Imagine standing between two facing mirrors, watching reflections stretch into infinity. Now replace those mirrors with universes, and the reflections with neutrinos flickering in and out of existence. Every time a neutrino disappears from our detectors, it might not be gone just visiting next door. Whether this mirror world is real or just a beautiful mathematical fantasy, the hunt for sterile neutrinos is forcing us to confront a profound possibility. The universe's symmetry might not just be hidden in equations, but in entire realities we've yet to see. What shape is the universe? Most of us picture it like an endless flat sheet, a vast cosmic plane stretching into infinity. But what if space isn't flat at all? What if it's curved like the surface of a balloon, or twisted into a shape as whimsical as a donut? This isn't just idle speculation. The universe's hidden geometry could rewrite our understanding of cosmic symmetry itself. Let's start with the simplest possibility, a flat universe. In this model, parallel lines never meet, and the angles of a triangle always add up to exactly 180 degrees. This is the geometry we learn in school, and it fits neatly with our everyday experience. But flatness isn't the only option. If the universe has positive curvature, like the surface of a sphere, parallel lines eventually converge and triangles bulge outward, their angles summing to more than 180 degrees. Picture two rockets launching side by side on a spherical Earth. If they travel straight ahead without adjusting course, they'll eventually collide, even though neither turn. Now imagine that on a cosmic scale, a universe where straight lines loop back on themselves. Then there's the wild card, the torus or donut shape. In this scenario, space wraps around in two directions, like a Pac-Man screen where exiting one edge teleports you to the opposite side. A toroidal universe wouldn't just bend, it would stitch itself into a seamless, repeating structure. Simulations of such a cosmos reveal eerie consequences. Look far enough in one direction, and you might see duplicate images of galaxy clusters, like reflections in a hall of mirrors. Light could circle the entire universe multiple times, creating ghostly afterimages of long-dead stars in the night sky. The real kicker: these topologies aren't just mathematical curiosities. They directly impact how symmetries play out across the cosmos. A spherical universe, for example, would have rotational symmetries in every direction, like a perfectly balanced spinning top. A torus, on the other hand, introduces translational symmetries patterns that repeat at regular intervals like tiles on an endless floor. Even the cosmic microwave background, the afterglow of the Big Bang, might hold clues. Scientists have scanned it for telltale repeating patterns, hints that space loops back on itself. So far, no definitive donut-shaped signatures have appeared, but the search continues. Critics argue that a flat universe fits the data best, but supporters of exotic topologies point to strange anomalies. Large-scale structures that seem to align in improbable ways, or temperature fluctuations in the cosmic microwave background that repeat suspiciously. Then there's the sheer scale of the mystery. If the universe is finite but unbounded, a sphere or torus too vast for us to perceive its curvature, we might never see the full picture, like ants crawling on a beach ball, mistaking its surface for an infinite plane. So why does this matter? Because topology doesn't just dictate shape, it defines the rules of reality. In a toroidal universe, a particle traveling far enough could return to its starting point, unchanged yet transformed, like a hero completing a mythic journey. Symmetries we take for granted might unravel or multiply in ways we're only beginning to grasp. Whether the cosmos is flat, spherical, or twisted like a pretzel, one thing's certain: the universe's true form is still hiding in plain sight, waiting for us to see beyond the obvious. At the heart of the Big Bang, time itself may have bent into a shape we've never seen, not a beginning, but a smooth curve where past and future merge like lines of latitude at Earth's poles. This is the no-boundary proposal, a radical idea from physicists James Hartle and Stephen Hawking that rewrites cosmic origins as a moment not of explosive birth, but of perfect symmetry. Imagine holding a globe in your hands. At the equator, lines of longitude run parallel, marking distinct north-south directions, but travel toward the poles, and those lines converge until, at the exact south pole, all directions become equivalent. Now replace latitude with time and the globe's surface with spacetime itself. Hartle and Hawking's insight was this: at the Big Bang, time may have acted just like those converging longitude lines, transforming seamlessly into space in a geometry with no sharp edges, no singularities, just an elegant, rounded-off universe where before loses all meaning. This isn't just poetic imagery. The math behind the no-boundary proposal treats the early universe's quantum state as a wave function, a probability distribution describing all possible configurations of spacetime. In most models, this wave function slams into a wall at time zero, the infamous singularity where physics breaks down, but Hartle and Hawking's version behaves differently. Their wave function naturally smooths out the singularity, like a painter blending a harsh line into a soft gradient. The result, a four-dimensional cosmos that's finite yet unbounded, where asking what happened before the Big Bang becomes as meaningless as asking what's south of the South Pole. Visual aids bring this to life. Picture a globe where the bottom tenth is sliced off and replaced with a rounded cap, no sharp edges, just a continuous curve. Now animate it. Latitude lines crawl upward, representing time's flow from the Big Bang, the South Pole, toward the present, the equator. Near the pole, these timelines are so tightly packed that distinguishing one moment from the next becomes impossible. There's no starting gun, no t equals zero, just space-time curving gently into existence, like a river emerging from a spring without any clear source. Critics argue this elegant solution glosses over quantum gravity's messy realities. After all, Einstein's equations still scream singularity when pushed to extreme densities. But supporters counter that quantum effects could smooth those infinities away, just as quantum mechanics prevents electrons from crashing into atomic nuclei. The no-boundary proposal doesn't erase the Big Bang, it redefines it as a transition rather than a creation, a moment where time's arrow wobbles briefly before pointing decisively forward. What's at stake here isn't just cosmology's origin story, but the very nature of time. If Hartle and Hawking are right, then the universe didn't arise from nothing. It arose from everything, a timeless, spaceless totality where directionality hadn't yet crystallized. The echoes of that primordial symmetry might still linger today, etched into the cosmic microwave background or hidden in the quantum jitter of empty space. Whether the no-boundary proposal survives future tests or not, it challenges us to see the cosmos not as a clock wound up and ticking down, but as a shape, mysterious, unbroken, and profoundly whole. In an infinite sea of universes, each bubble might freeze into its own unique pattern of broken symmetries, like countless pans of water crystallizing into snowflakes, no two alike. This is the multiverse's answer to one of physics' deepest riddles. Why do the constants of nature, the strength of gravity, the mass of an electron, seem so exquisitely fine-tuned for life? The answer could lie in cosmic chance, a roll of the dice during symmetry, breaking moments when newborn universes cooled from searing chaos into order. Picture the early cosmos as a scalding quantum foam, buzzing with every possible symmetry. As each pocket of spacetime inflated into a universe, it underwent phase transitions like steam condensing into water, then freezing into ice. But here's the twist. Just as ice crystals form differently depending on impurities or temperature fluctuations, each universe's symmetries might have fractured in random directions. In ours, the Higgs field froze in a way that gave particles just the right masses for atoms to form. Another universe might have locked in a Higgs value so weak that matter couldn't clump into stars, or so strong that everything collapsed instantly into black holes. These fractures aren't arbitrary, they're sculpted by mathematics. The dynamical systems governing symmetry breaking resemble a ball rolling down a mountain with multiple valleys. The exact path it takes, which valley it settles into, depends on tiny quantum jitters during the descent. Inflation theory suggests our observable universe is just one patch in a vast mosaic, each region landing in a different valley with its own physics. Some might have 4 fundamental forces, others could have 6 or more. Some might permit time to flow backward in pockets, others could be so symmetric that particles never gained mass at all, rendering them featureless and sterile. Critics argue this smacks of cosmic luck, but proponents counter that it's statistics. With enough trials, even the rarest outcomes become inevitable. The anthropic principle sharpens the argument. We only observe a universe compatible with life because, well, here we are. Telescopes can't peer beyond our cosmic horizon to test this directly, but subtle fingerprints might linger. If adjacent bubbles collided during inflation, they could have left bruises in the cosmic microwave background, anomalous cold spots or strange polarization patterns. Some theorists even hunt for evidence in the distribution of galaxies, searching for unnatural alignments that might betray a neighboring universe's gravitational tug. Visualize the multiverse as a frothing ocean, each bubble universe a rising bubble with its own distinct shimmer. Most are dark, barren, governed by broken symmetries that stifle complexity. A rare few, like ours, strike a fragile balance, just enough asymmetry to birth galaxies, but not so much that chaos reigns. Whether this vision holds or collapses under scrutiny, it reminds us that the laws we call fundamental might just be local bylaws, quirks of our cosmic neighborhood. And somewhere out there, in the infinite foam of reality, another version of physics is playing by entirely different rules. What if time isn't fundamental at all, just a comforting illusion woven into the fabric of our perception? The Wheeler-DeWitt equation, a bold attempt to unify quantum mechanics with general relativity, suggests exactly that. In this radical framework, the universe isn't a dynamic, evolving entity but a frozen, 4-dimensional sculpture, a cosmic block where past, present, and future exist simultaneously, locked in perfect symmetry. The equation itself reads like a paradox. Unlike Schrödinger's wave equation, which describes how quantum systems change over time, the Wheeler-DeWitt equation lacks any time variable at all. It's as if someone took the ticking clock out of physics' most fundamental machinery. John Wheeler and Bryce DeWitt, wrestling with Einstein's gravity and quantum uncertainty in the 1960s, landed on this startling conclusion. When you treat the entire universe as a quantum object, time vanishes from the equations. Not slows down, not becomes relative, disappears entirely. Visualize this with a thought experiment. Imagine filming a sunset, then pausing the video on a single frame. In that frozen image, the sun isn't rising or setting, it simply is. The Wheeler-DeWitt universe treats reality like that paused frame, but in 4 dimensions. Every event, the Big Bang, the formation of stars, your first breath, exists eternally within the block, like fixed points in an unchanging mosaic, the flow of time. Just a trick of consciousness, a story our brains tell to navigate the static structure. This leads to the infamous problem of time. If fundamental physics has no time parameter, why do we experience such a vivid, unshakable now? Some theorists argue time emerges from quantum entanglement, a collective illusion created by particles correlating their states. Others suggest it's a thermodynamic artifact, the universe's slow march from order to disorder, creating the arrow we perceive. The most radical interpretation, that change itself is a superficial layer over a deeper, timeless reality. Picture the cosmos as a vast, unchanging crystal. From inside, we're like ants crawling along one facet, mistaking our limited path for a flowing river. The equations insist there's no river, just an infinite, interconnected structure where every moment is equally real. Whether this vision holds or crumbles under scrutiny, it forces us to confront a haunting possibility. The universe's greatest symmetry might be its silence, a frozen perfection where time is the one variable we invented to make sense of the stillness. Magnets have their north and south poles, and electricity comes with neat positive and negative charges, but gravity has always been the odd one out, stubbornly refusing to play by the same symmetrical rules. What if we've been missing something crucial? Enter the gravitomagnetic monopole, a hypothetical particle that could rewrite our understanding of gravity by giving it its very own north pole without a matching south. This isn't just science fiction, it's a serious proposal that could stitch gravity and electromagnetism together into a single, elegant framework. Imagine space-time not as a blank canvas but as a kind of cosmic ferromagnet, with invisible lines of gravitational charge threading through it like the microscopic domains in a bar magnet. Just as electric charges create magnetic fields when they move, mass in motion generates gravitomagnetic fields, subtle twists in space-time predicted by Einstein's general relativity. But here's the twist. If gravitomagnetic monopoles exist, they'd be pure sources or sinks of this gravitational twist, unmixed with anything else. Picture a whirlpool in space-time that only swirls inward, with no outward flow to balance it, a gravitational anomaly that defies the usual symmetry. Why does this matter? For one, it could solve a glaring asymmetry in physics. Electromagnetism enjoys perfect duality between electric and magnetic phenomena, but gravity has always seemed lopsided. Monopoles would restore that balance, suggesting a deeper kinship between these fundamental forces. Some theories even suggest that gravitomagnetic monopoles could be relics of the early universe, forged in the searing heat of the Big Bang when gravity and electromagnetism might have been unified. Detecting these elusive entities is another story. Unlike their electromagnetic cousins, gravitomagnetic monopoles wouldn't interact with light or matter in obvious ways. They'd warp spacetime itself. That's where LIGO, the Laser Interferometer Gravitational Wave Observatory, comes in. By monitoring the ripples from colliding neutron stars, physicists hope to spot anomalies in the gravitational waves, subtle hiccups that might betray a monopole's presence. Think of it like listening to a symphony and suddenly hearing a note that shouldn't exist, a vibration with no counterpart in the score. The implications are staggering. If monopoles are real, they could be the missing link in a grand unified theory. a clue that gravity isn't the outsider we thought but part of a larger symmetrical tapestry. Even if they're never found, the search itself stretches our understanding of space-time, forcing us to ask, what other hidden symmetries might be woven into the universe's deepest layers? Classical physics tells us that any charged particle moving in a circle should radiate energy like a miniature lighthouse, its light dimming as it loses power. Yet electrons orbiting atomic nuclei do precisely the opposite. They whirl endlessly without shedding a single photon. This cosmic defiance of electromagnetic symmetry puzzled scientists for decades until quantum mechanics revealed a breathtaking truth: the electron isn't really orbiting at all. It's standing still while simultaneously being everywhere at once. Picture a jump rope held at both ends, vibrating in perfect waves that never travel forward or backward, just up and down in place. This is the electron's reality inside an atom, not a planet circling a star, but a quantum standing wave trapped between the nucleus's pull and its own wave nature. Niels Bohr first glimpsed this strange stability in his atomic model, where electrons occupied fixed orbits like rungs on a ladder, their energies quantized into discrete steps. But Bohr's neat planetary orbits were just the beginning. Modern quantum theory paints a far wilder picture: probability clouds where an electron exists as a haze of possible locations, its position defined not by a path but by peaks and troughs of likelihood. The key lies in wavelength synchronization. For an electron's wave to perfectly fit around a nucleus without canceling itself out, the circumference of its orbit must equal a whole number of wavelengths, like fitting exactly 3 waves into a circular track. Only at these precise distances can the electron's wave reinforce itself constructively, creating stable orbitals where energy loss becomes impossible. Step outside these golden ratios and the wave collapses. This explains why electrons occupy specific shells and why they don't spiral into the nucleus despite their opposite charges. They're not particles being flung outward by centrifugal force but waves trapped in resonant harmony. Compare this to sound in a cathedral. Sing a single sustained note, and certain spots in the room will hum with amplified resonance while others fall silent, not because the sound is moving, but because the architecture shapes the wave. Atoms do the same for electrons, their electric fields sculpting quantum standing waves into shapes as intricate as dandelion fluff or dumbbells, the famous S orbital. A perfect sphere of probability, the p orbital, a twin-lobed figure 8 humming with directional asymmetry. What shattered classical symmetry wasn't a flaw in nature but a limitation in our intuition. Electrons don't break the rules, they follow deeper ones, where particles dissolve into probabilities and motion blurs into stillness. The radiation that should pour from their orbits doesn't vanish. It's preempted by the universe's quantum fine print, a clause stating that waves in perfect resonance exist outside time's usual accounting. Seen this way, the atom isn't a tiny solar system but a frozen symphony, its notes held eternally in place by the mathematics of harmony itself. What if the universe isn't just governed by physics but by something eerily close to artificial intelligence? Picture the cosmos not as a collection of particles or waves, but as an unfathomably vast neural network, with every galaxy, star, and atom acting like a neuron firing in a cosmic brain. This isn't science fiction, it's a bold theory proposed by physicist Vitaly Vanchurin, who suggests that space-time itself might emerge from a deep learning structure, the universe's underlying code humming with the same patterns that power our most advanced eye. Think of the cosmic web, those sprawling filaments of galaxies stretching across billions of light years. Under a microscope, they look uncannily like the synaptic connections in a human brain, with dense galaxy clusters mirroring neural nodes and wispy filaments resembling axons. Vanchurin's model takes this resemblance seriously. In his framework, particles aren't fundamental. They're the output of a neural network's hidden layers, their properties emerging from the weights and biases of cosmic-scale computations. Even time could be an illusion, a side effect of how information propagates through this network, like the sequential layers of a deep learning algorithm adjusting its parameters. The implications are staggering. Just as a trained neural network recognizes patterns in data, say, distinguishing cats from dogs, the universe's network might learn the laws of physics through cosmic evolution. Van Choren's equations suggest that what we call gravity or quantum mechanics could be stable attractor states, the universe's equivalent of a machine learning model converging on an optimal solution after epochs of training. Black holes may be their overloaded neurons, regions where the cosmic network's gradients grow so steep they collapse into singularities. The Big Bang itself could be the moment this neural architecture booted up, its initial randomness crystallizing into the orderly symmetries we observe today. Skeptics argue this is just a provocative metaphor, but Van Choren points to eerie parallels. In machine learning, tiny changes in initial conditions, like the random weights assigned at startup, can lead to vastly different outcomes. Sound familiar? It's the butterfly effect on a cosmic scale, reminiscent of quantum fluctuations seeding galaxy formation. Even entropy, the universe's march toward disorder, finds a counterpart in neural networks' tendency to minimize loss functions, drifting toward equilibrium. But here's the real mind bender. If the universe is a neural network, who or what is the programmer? Van Choren sidesteps the metaphysical trap by suggesting the network might self-organize, its architecture emerging from mathematical necessity. Imagine a child's kaleidoscope where simple rules generate infinite complexity. The universe's code could be equally minimalist, its apparent sophistication arising from iterative processes we're only beginning to decode. Visualize this with a cosmic thought experiment. Zoom into the fabric of spacetime past quarks and quantum foam until you reach a lattice of interconnected nodes. Each node processes information, its output shaping the behavior of its neighbors. Now pull back, way back, and watch as these micro-interactions scale up to create the forces, particles, and symmetries we call reality. The equations governing this network might look nothing like Einstein's field equations or Schrödinger's wave function, yet they could approximate them so precisely that the difference is philosophical, not practical. Whether this neural universe theory holds up or not, it forces us to confront a radical possibility. The symmetries we've spent centuries uncovering might not be fundamental laws but emergent properties, the universe's way of optimizing itself. The next time you gaze at the night sky, consider this: you might not just be looking at stars. You could be staring into the synaptic firings of a cosmic mind, a structure so vast and ancient it makes our most advanced eye look like a child's scribble. And if Van Choren is right, the universe isn't just governed by math, it is math unfolding in real time. The Big Bang paints a dramatic picture, a singular moment when the universe erupted from infinite density, birthing time, space, and all we know. But what if that wasn't the beginning? What if our cosmos is just the latest breath in an endless cycle, expanding and contracting like a cosmic accordion, each collapse not an end but a reset wrapped in perfect symmetry? This is the self-similar Big Bounce, a vision where the universe doesn't die with a whimper or a crunch, but rebounds, preserving its deepest patterns across eons. Loop quantum cosmology, a daring offshoot of quantum gravity theory, offers a mathematical blueprint for this cyclical rebirth. Imagine spacetime not as smooth fabric but as a woven tapestry of tiny, indivisible threads. Near the Big Bang's extreme densities, these threads resist further compression, creating a repulsive force stronger than gravity itself. Instead of collapsing into a singularity, the universe reaches a minimum volume, a quantum bounce, where contraction flips seamlessly into expansion. Picture squeezing a rubber ball with all your might, only for it to rebound the instant it touches a hidden spring inside. The Big Bang wasn't a beginning but a turning point, a moment when a prior universe's collapse inverted into our own expansion. The magic lies in what's preserved. In most cyclic models, entropy, the universe's disorder, would grow with each cycle, eventually drowning all structure in chaos. But the self-similar bounce suggests a deeper symmetry. Just as fractal patterns repeat identically at every scale, the post-bounce universe could mirror its predecessor's fundamental geometry. Constants like the speed of light or Planck's length remain unchanged, while quantum fluctuations imprint eerily similar galactic seeds in each new cycle. Astronomers might one day spot these echoes in the cosmic microwave background, ghostly concentric rings representing collisions from a universe before ours. Critics argue this requires fine-tuning beyond plausibility, but supporters point to loop quantum gravity's natural avoidance of singularities. In this framework, the universe doesn't forget its past, it recycles it like a phoenix rising from ashes with the same elemental blueprint. Even time behaves differently here. Instead of an arrow, it's a pendulum, swinging between expansion and contraction without a definitive start or end. The equations hint at a cosmic déjà vu, where every cycle isn't just similar but symmetrically entangled with the last. Visualize this with a thought experiment. Shuttle a video camera through a bounce. Galaxies would redshift as space contracts, then blueshift as it rebounds, their light stretching and squeezing like notes from an accordion. Matter wouldn't annihilate but transform, its quantum information preserved through the transition like a flame passed between candles. The result, a universe eternally renewing itself, not through repetition but through resonance, each iteration a variation on a timeless theme. Whether the Big Bounce is real or not, it challenges our obsession with origins. Perhaps the universe isn't a story with a first chapter, but a song with infinite verses, each chorus echoing the last in perfect, self-similar harmony. At the very edge of our understanding, where the fabric of spacetime frays into quantum foam, physicists hunt for cracks in reality's most unshakable symmetry. Lorentz symmetry, the principle that the laws of physics remain identical no matter your speed or direction, has been a cornerstone since Einstein. But what if it's not perfect? Some quantum gravity theories suggest that at unimaginably small scales, near the Planck length, spacetime itself might churn like a stormy sea, creating minuscule violations in this cosmic invariance. These tremors could be our first direct glimpse into a theory of everything. Gamma-ray bursts, the universe's most violent explosions, serve as accidental laboratories for testing this. When these beams of high-energy light race across billions of light-years, even the tiniest Lorentz violation would leave fingerprints. Photons of different energies should stagger slightly, like runners on a bumpy track. In a perfect universe, they'd arrive in sync. But if spacetime foam disrupts their journey, the highest energy photons might lag behind. NASA's Fermi Gamma-Ray Space Telescope has spent years analyzing these delays, hunting for deviations that could rewrite physics. Zoom in further, past atoms, past quarks, down to the Planck scale, a realm where spacetime isn't smooth but a seething froth of virtual black holes and wormholes. Here, the very concept of distance might dissolve into quantum uncertainty. Some models suggest this foam could act like a hall of mirrors for light, twisting polarization or scattering particles in ways that subtly break Lorentz symmetry. Experiments using ultra-precise atomic clocks or polarized light from distant quasars seek these anomalies. Imagine a clock ticking differently depending on its orientation. A violation so small it's like detecting a single grain of sand shifting on a distant beach. The stakes couldn't be higher. If Lorentz symmetry holds perfectly, it's a dead end for many quantum gravity theories, but a single confirmed fracture. That's a crack in reality's foundation wide enough to peer into the universe's deepest workings. Whether these searches succeed or fail, they remind us that even the most sacred symmetries might be provisional, waiting for the right experiment, the right burst of gamma rays to reveal their hidden flaws. Galaxy clusters shouldn't move like synchronized swimmers, not in a universe that's supposed to be homogeneous, where matter spreads evenly in all directions. Yet that's exactly what astronomers witnessed in 2008. Hundreds of massive galaxy clusters, each weighing a quadrillion suns, streaming en masse toward a single patch of sky at blistering speeds over 700 kilometers per second. This bizarre cosmic current, dubbed the dark flow, defies everything we know about the post-Big Bang expansion. If the universe is isotropic, the same in every direction, why are these clusters all rushing toward what appears to be nothing? The Planck Space Telescope's velocity maps reveal the mystery in startling detail. Like tracking leaves caught in a hidden river, Planck's measurements showed galaxy clusters drifting uniformly toward a point beyond the observable horizon. The oddest part, this motion can't be explained by known gravitational forces. Even the pull of the Shapley supercluster, the largest concentration of matter in our cosmic neighborhood, accounts for less than half the observed velocity. Something far more massive, something beyond the edge of our visible universe, must be yanking these clusters toward it. Theories range from the tantalizing to the terrifying. Some suggest a supermassive structure in an adjacent bubble universe, its gravity leaking through space-time like a magnet tugging iron filings through paper. Others propose our universe collided with another during inflation, creating a titanic dent in cosmic geometry that still funnels matter inward, the most radical idea. That the dark flow points toward the epicenter of a higher dimensional event, a gravitational shockwave rippling through the multiverse. Critics argue the data might be statistical noise, but the signal persists across multiple studies. If real, this motion violates the cosmological principle's sacred symmetry, revealing a universe far stranger than we imagined. Whatever's out there, lurking beyond the cosmic veil, it's rewriting the rules of isotropy, one invisible tug at a time. The dark flow doesn't just hint at unseen mass, it suggests our universe might be a single stitch in a much larger, asymmetrical tapestry. Imagine floating alone in an infinite void, no stars, no planets, just darkness stretching forever. Now picture this, your brain, fully conscious, spontaneously assembling from random quantum fluctuations, complete with fabricated memories of a life that never existed. This isn't a horror story, it's the Boltzmann brain paradox, a thought experiment so unsettling it challenges whether our entire universe is more likely to be a fluke than a cosmic inevitability. The paradox emerges from Ludwig Boltzmann's 19th century work on thermodynamics, where he realized even the most disordered systems occasionally stumble into order by sheer chance. Apply this to cosmology, and the math takes a bizarre turn. In an eternal, chaotic universe, random fluctuations could theoretically conjure a self-aware mind like yours far more easily than crafting an entire ordered cosmos. After all, assembling one brain requires infinitely fewer particles than arranging galaxies, stars, and planets. Statistically, you're more likely to be a momentary accident, a Boltzmann brain, than a product of 13.8 billion years of evolution. Critics argue this reduces reality to absurdity. If consciousness can blink in and out of existence, how could any observation be trusted? Your memory of eating breakfast today might be a phantom imprint, and the device you're watching this on could vanish the instant this thought forms. The paradox forces physicists to confront an uncomfortable question. Does the universe's symmetry favor chaos over structure, randomness over design? Yet there's a loophole. If the cosmos is fundamentally finite, if it had a definitive beginning and will have an end, the probability of Boltzmann brains plummets. This is one reason many theorists cling to the Big Bang as a cosmic reset button. An infinite, unchanging universe, on the other hand, becomes a hall of mirrors where self-aware illusions inevitably outnumber real, ordered worlds. The debate rages, but one thing's certain. The Boltzmann brain paradox doesn't just question reality's structure, it questions whether questioning reality is even meaningful. So next time you gaze at the night sky, consider this: the stars might not just be distant suns. They could be your brain's desperate attempt to fill the void, a fleeting mirage in an ocean of nothingness. Or maybe, just maybe, they're proof that symmetry sometimes loses to structure, and that we're here because the universe dared to be more than chaos. Go back to the first time you solved a math problem, really solved it. That moment when numbers stopped being symbols on a page and clicked into place like a lock turning. Now stretch that feeling across the entire cosmos, and you've glimpsed the mathematical universe hypothesis. At its heart lies a radical idea. Reality isn't just described by mathematics, it is mathematics. From the spin of an electron to the spiral of a galaxy, everything we call physical might just be relationships between abstract structures, shadows cast by equations we're only beginning to decipher. Max Tegmark, the hypothesis's boldest champion, takes this further. He argues that symmetry isn't just a feature of the universe, it's the foundation. Think of a perfect dodecahedron, its 12 pentagonal faces folding space into a cosmic origami. Tegmark suggests our entire cosmos could be shaped this way, with the geometry of spacetime stitched together by mathematical constants so precise they hum with inevitability. The equations governing quarks and quasars, not human inventions but discoveries, eternal truths waiting in a Platonic realm independent of physics. Visualize this by overlaying the cosmos with its hidden equations. A supernova's explosion traces the arc of differential calculus. The orbits of planets sketch Fourier transforms in the void. Even the chaotic dance of quantum particles resolves into elegant matrix algebra when viewed through the right lens. The kicker: if math is the true substance of reality, then every symmetry, from the simple mirroring of a snowflake to the intricate Lie groups governing particle physics, isn't just beautiful. It's ontology. Critics argue this reduces existence to a sterile abstraction. Where's the room for consciousness, for qualia, in a universe of pure numbers? Tegmark counters with a thought experiment. Imagine a self-aware subroutine in a vast computer simulation. Its experience emerges from the computation's logic, no less real for being mathematical. The implications spiral outward. If the universe is fundamentally mathematical, then every possible consistent structure exists somewhere in the multiverse. A cosmos where pi equals 4, a reality built on hyperbolic geometry, all equally valid, all out there in the ensemble of mathematical existence. Now consider the cosmic microwave background, the afterglow of the Big Bang. When scientists mapped its fluctuations, they found suspiciously regular patterns, as if space itself were a finely tuned resonator. Some analyses even suggest these patterns align with the symmetries of a dodecahedral universe, where light wraps around closed geometry like a hall of mirrors. It's speculative but tantalizing. What if we're all living inside a shape so perfect, its angles and edges whisper the universe's truest name? The allure of Tegmark's vision isn't just its audacity, but its economy. No need for unseen dimensions or hidden variables, just math, pure and self-sufficient. Whether this hypothesis holds or collapses under scrutiny, it reframes our search for symmetry from a scientific pursuit to something deeper. The universe revealing itself not as a collection of objects, but as a tapestry of truths woven in numbers we're only beginning to read. So the next time you balance a checkbook or measure a right angle, remember, you might not just be doing math, you might be touching reality's bedrock. From the quantum foam churning beneath spacetime's surface to the golden spirals stretching across galaxies, symmetry isn't just a pretty pattern, it's the universe's hidden language. Think about the eerie dance of entangled particles, defying distance as if space itself were an illusion. Or the Higgs field's grand phase transition, freezing into broken symmetry to give mass to everything from electrons to entire stars. These aren't isolated curiosities, they're clues scribbled across every scale of reality, whispering that chaos might just be a facade over something far more elegant. Take the holographic principle, where entire universes could be projections from a flat, two-dimensional surface. Or the octonions, those eight-dimensional numbers that might stitch together the extra dimensions string theory demands. Even time itself, which feels so absolute, could be an emergent illusion, a side effect of deeper symmetries we're only beginning to untangle, the wildest part. These ideas aren't poetic metaphors, they're testable, measurable, and in some cases already leaving fingerprints in data from colliders and telescopes. This is where science transcends mere observation and brushes against philosophy. Every broken symmetry, from the matter-antimatter imbalance to the fractal wrinkles in galaxy clusters, hints at a cosmos far stranger than we imagined. The hunt for a theory of everything isn't just about unifying equations, it's about decoding the universe's love letter to geometry, written in the spin of particles and the curve of spacetime. So here's the challenge: look around, notice the symmetries in a spiderweb, the Fibonacci sequence in a pine cone, or the way shadows and light mirror each other at sunset. The universe is showing its hand, and we're learning to read it. Now it's your turn. Which symmetry stops you in your tracks? Drop your favorites below, and let's keep unraveling the cosmos together. After all, the next great discovery might start with a single observation, maybe even yours.